All right. Good morning. Good morning. Come on.
Good morning.
All right. Let's do a quick check. So race car. UAV. Okay. UAV sour. Cogworks. 3D printing. And embedded security. CubeSat. Metalytics. So CubeSat and the Metalytics classes today are at the visiting Lincoln Laboratory. So next year, hopefully, maybe we can all have you visit, but that's where they are. So today, we have another great talk by Professor Asu Ozdaglar. She received her bachelor's degree in electrical engineering from Middle East Technical University at Ankara, Turkey, and received her master's and PhD from MIT in the Department of Electrical Engineering and Computer Science. She's the Joseph and Nancy Keithley Professor of Electrical Engineering at MIT, and she's also the department head. She is a recipient of many awards, which you can see in her bio, so I won't go through them. But with that, let's give her a warm welcome.
Thank you very much, Bob, for the invitation. It's a pleasure to be presenting to this dynamic group. Welcome to MIT. I hope you're enjoying your time here. It's a very dynamic, wonderful place, so I hope you found it as productive and prolific as we do. As Bob mentioned, I'm from the Department of Electrical Engineering and Computer Science. It's a very large department, the largest of MIT. We have a lot of students. We basically teach about 40% of the whole undergraduate population at MIT. So it's a big department. It's organized around different labs, 4 big labs. You may have heard about these. There's the CSAL, LIDS, RLE, and MTL with different focus areas in research. I belong as a faculty member to the Laboratory for Information and Decision Systems, and that's sort of the LIDS. I don't know if you heard it before. I guess Sertaç is teaching, Sertaç Karaman. That's another faculty member in LID. It's an interdepartmental lab, so it has faculty members not just from EECS, but from other engineering departments at MIT. And the focus is basically analytical information sciences. So focuses on coming up with fundamental theory, algorithms to be able to analyze information and decision systems. So I think much of what you've been focusing on is related to the research done in LIDS. So what I work on is optimization and decisions in large-scale systems, networks, and also data processing. And today I'll just try to give you, because this is a short talk, I said, maybe I'll give them a highlight of the type of work I do, sort of motivate them about the problems that I find very exciting and interesting. So just quickly, if you're thinking about why decisions and optimization, it arises in many, many different applications, not just in EECS, but many, many different places. So maybe a prominent example, this is why I think it sort of holds a place in EECS, is the data and computer networks. So think about a very big computer network where we have millions of computers connected to each other through links and routers and support applications like email, file transfer, audio, video. Here, the goal is for efficient operation of the system is to be able to do resource allocation. So you have these data packets you need to send around among computers, and how do you route these data packets? How do you do scheduling? How do you do efficient communication? So that's sort of the goal that arises in these network environments. Signal and image processing. So you ask questions about how do I design a filter, array. And a very sort of popular recent application is compressed sensing. You may have heard about this. This is about how do you efficiently acquire and reconstruct sparse signals using much fewer measurements than is used typically. So that's sort of the idea of compressed sensing, which is essentially can be formulated in a nice optimization formulation. Communication, transmitter, receiver designs for MIMO systems, power control, but also, as I mentioned, this is not just in engineering, also in business applications such as manufacturing, operations research, supply chain revenue management, financial engineering. Many of these sort of areas have lots of problems where they benefit from optimization formulations and algorithms for their solutions. So what do I do? I mean, sort of optimization is a mature area. If you look at the traditional approach, there are some characteristics. First of all the information you need to be able to come up with these optimization formulations and decisions is centralized. And the problem sizes are moderate to large. So you have, moderate is like 100 to 1,000 decision variables that you're trying to figure out. What is the optimal way of choosing these decision variables. There's a single optimization objective. I gave you the example of data networks. So you can actually think about with a single control objective, how do I design a routing algorithm to minimize congestion or delay in this network? So that has been the focus of optimization for the past many years or decades. But if you look at the past decade, we now have modern systems and applications that pose new challenges. The first challenge I'd like to highlight is that now information is decentralized because many of these systems are very large scale. And they collect data in a decentralized manner. They actually serve agents with very heterogeneous and privately known restrictions and requirements. So one example I put down there is sensor networks. You have many sensors that are sort of spread around. They collect information. And from that information, you would like to process it and come up with a model or whatever you want to do with the data. The second factor which is important is a driving force. The technological advances in online platforms as well as automated markets allowed us to be able to collect very large data sets. And this sort of leads to very large problem sizes. So remember I said moderate to large was 1,000 decision variables. Now think about decision variables of size 10 to the 6, 10 to the 8. So those are the problem sizes that we are dealing with. And this final thing I'd like to also highlight is that, remember, when I was talking about single objective, minimize delay. If you look at the systems of today, they're not controlled by a single entity. These are interconnections of many autonomous entities, and they also serve active strategic users. There are many examples of this. The example I sort of like highlighting is a smart energy grid system. So this is basically a system that consists of competing generators, a transmission network or transmission lines controlled by ISOs, distribution lines controlled by utility companies, and also residential customers who also participate in this market in an active manner now through demand management mechanisms or think about direct load control, indirect load control, renewables. So this is now a very decentralized system with multiple entities, each with their own objectives. So there's not a single objective that I can just take and try to optimize. So this changes the formulation and the optimization question significantly. And the final thing I'd like to highlight is that networks become a very important consideration. The interconnectivity structure of these systems becomes an important consideration in how these systems operate. So both in the context of technological systems, namely if you look at a power grid or a traffic network, how this traffic network is laid out or what the interconnection is has an important role in the overall congestion levels and the operation of the system. And the other place where this network structure sort of emerges is now in economic and financial systems. Interestingly, many of the economic markets are no longer functioning as anonymous markets in which everybody is interacting with everyone else, but they look like networks. So I can give you many examples. I pulled here a particular example from the Bureau of Economic Analysis. This is basically depicting the linkages between the US sectors. So think about these sectors as agriculture, automotive systems, glass, and there's a link between them if these sectors use the output of the other as input or intermediate good for the output that they're producing. So there's this coupling, which very much looks like a very sparsely connected network there as well. So if you want to understand the economic outcomes, the network structure becomes an important consideration in figuring out the operation. And the same thing in financial systems. So this basically motivated new methods for optimization and control of these systems. In particular, we need very fast and scalable algorithms to process these huge dimensional data sets. We want our algorithms to operate in a decentralized manner. We can't rely on data to be only in one place. And moreover, we would like to recognize also the role of this human element in the operation of these systems. Remember the smart grid energy system I mentioned, and its dynamic interaction with the underlying network structure. And my group, research group, basically develops models, mathematical tools, and algorithms to analyze such systems, control such systems, and also come up with algorithms for large-scale data processing. And I find this a very exciting area because it basically doesn't sit within one discipline. I hope my examples was able to convey that this is at the intersection of engineering, computer science, economics, operations research, and social sciences. And the tools that we use are things like optimization and control theory, graph theory to model this network structure, stochastic network analysis, as well as economic modeling and game theoretic models. So to give you a sense of what research looks like in this space, in this talk, what I'll do is I'll first talk about evolution of fast methods for optimization driven by this technological change. I'll tell you a little bit about the excitement in optimization in the 80s and 90s, which are these sophisticated interior point methods, to this very simple computational cheap gradient methods. That's the focus of optimization community right now. I'll say a little bit about our recent work on how we sort of develop these fast and scalable methods for both data processing and decentralized optimization over networks. I'll briefly talk about sort of how do we think about optimal control policies or algorithms for containment of contagious processes. This could be epidemics, an epidemic spreading throughout the population through a contact network, or it could be failures in a financial system spreading dynamically, and you have limited resources, you want to control this, how do you do it in an optimal way, okay? And finally, I will not have much time to go into this, but I'll try to also give you a flavor of some questions where we really need game theoretic models to capture this autonomous agent behavior, and how game theoretic models can help us design incentives for control of these systems, okay? So I'll try to give maybe a high-level idea of many of these things. I won't go into the details, both because of time and we need some more tools to be able to go into the details, but I'll just try to give you highlights of main ideas of how progress has been made in this area over the years, very much driven or coupled with the needs of the technological advances. So let me start by sort of this excitement I mentioned to you. There's been a lot of progress on fast methods for convex optimization. And many people think about the revolution as the development of these interior point methods. I'm not going to tell you what they are, only that they're very sophisticated, requires quite a bit in terms of their design and operation. And, this basically revolutionized the optimization theory and practice, because the key term you need to remember from this is that these were polynomial time algorithms. So what that means is, provably, theoretically, these algorithms' runtime is polynomial in the problem size or dimension. So think about this as n to the k. Versus an exponential time, which is bad. This is the brute force of figuring out what each of these decision variables should be, right? So let me be a little bit, drastic here. Think about this k as 1, and let's say our problem dimension is 100. So we're talking about 100 to the 100 steps versus 2 to the 100 steps. And that's a huge difference in terms of runtime. And the important piece of this is we're thinking about, all kinds of problems, right? This is provably polynomial time for any problem of dimension n. So that was the revolution. And the other point I'd like to highlight is that this revolution actually came from a 28-year-old mathematician called Karmarkar, who was working at the time at AT&T Bell Labs. And I put some news clips at the time. These are from Time magazine. I don't know what this is, but from '84. And basically, I highlighted a quote from here. It says, breakthrough is one of the most abused words in science, says Ronald Graham, director of the mathematical sciences at Bell Labs. But this is one situation where it's truly appropriate. And you can't see these clips, but basically it's very interesting because it talks about all diverse areas and disciplines that are very interested in this new technology. It talks about American Airlines trying to grab this new algorithm to be able to do their scheduling for, at the time, their 1,000 planes, 80,000 passengers, 4,000 crew. So this is a hard problem. I mean, I hope you're sort of trying to get why I'm excited about optimization. You have all these different dimensions that you try to schedule. You try to operate this airline, right? You have to schedule planes, you have to schedule passengers, crew, and it's very large dimensional. So this algorithm is of great interest to American Airlines, but not just in that sector. Another example that's given here is investment companies that are super interested in this, because they would like to come up with the best mix of portfolios that consists of optimal mix of stocks and bonds. That's another optimization problem that you can actually formulate and solve. This is very large dimensional, again, using this technology. So this was a breakthrough. And if you, again, I would like to highlight, the important point is that provably this is polynomial time. So for any problem, you will actually produce high accuracy solutions very fast. But if you look at the practice of it, the running time is polynomial in n, but it depends on n. And it actually, if you look at many interior point methods, it's something like n cube. So for moderate problem sizes, 1,000 and whatnot, this is reasonable. But starting 2000s, problem sizes become exploding. So if you're thinking about, for instance, this is a nice paper that I like that sort of starts questioning the interior point methods. It looks at an imaging problem. This is a PET imaging problem, so they just scan and use the data to generate these images. And if you're interested in I believe this is a 64 by 64 resolution image that corresponds to an n equals 250,000, an iteration of this algorithm takes 2.5 hours. If you go to a little bit more higher resolution, 128 by 128, one iteration takes 2 weeks. So you don't want to wait that long to construct an image. Okay? So single iteration can last forever. People started sort of questioning interior point methods. And we see, this was the early 2000s, right? We see an increase more and more as we sort of have new technologies in acquisition and storage, as well as these online platforms. The data we acquire is huge, whether it's tick-by-tick financial data, whether it's image-by-image surveillance data from high-resolution surveillance systems. So data sets are large, hundreds of millions, billions of data points or examples. Data is high-dimensional. So this now motivated us to use simple algorithms. We want algorithms which are simple, which are basically dimension independent. So we don't want it to depend on dimension. And we don't want high accuracy solutions. We want some good solutions that we can produce fast. Okay? So that sort of turned around the community. And now, if you look at the optimization community, which is a large community, all we do is gradient methods. These are the simplest. I think it goes back to Lagrange, maybe 300 years ago, but this is what we do now. Very simple methods, which sort of takes a point, evaluates the gradient of the cost function, and moves in that direction. So another point is that many of these data processing problems can be formulated this way. Minimize some cost function, f, and the f generally takes the form of a sum. Okay? So these are structured problems that can be written as this sum. These fi's are all convex functions. Now think about this m as the size of your data set. So per data point, or data block, you have one component there. So, and this fi is the loss function associated with one data point. And now how many data points we have? 10 to the 8. So this is a sum over 10 to the 8 data points, okay? And in the applications that I keep talking about, both this dimension of the problem n and m are large. So this is the formulation we're going to work with. It sounds a little abstract, so just to put it in context, let's pick up an example, a machine learning example. You may have seen in several courses here that machine learning is a very popular area right now. We have machine learning courses in our department. It's taken by 700 students. So very popular. This is a baby example, okay? But it, I think, conveys the message. So here's the data. So I have some feature vectors, and I have some target output yi. And this is over, many data points. M is my number of data points. Let's say, let's give it some concrete example. Let's say we're trying to come up with an electricity demand model, a prediction of how much electricity will be demanded in this region as a function of the temperature. Okay, those are my data points. So I have some examples, like at this temperature, this was the demand. At this temperature, this was the demand. And I would like to come up with a model that can predict this automatically. Okay? Let's say that my model is a three-dimensional polynomial. Okay? Here is the model. So it has some coefficients. It has the temperature, right? So give me the temperature. This will spit out a demand for you. That's the output of the model. And the question that I'm trying to figure out is, what's the best model that can explain this data and hopefully help me with prediction when new data comes in? That's the idea. So this is the three-dimensional polynomial that I'm trying to fit here. So how do I formulate this? I'm trying to find the best fit to data of these coefficients, x0, 1, 2, 3. So I'm trying to find the best x to minimize the difference between the prediction of my model and data. If you haven't seen this before, it may take a while, but I think the point I'm trying to make it is many of these prediction problems, regression problems, are formulated in this nice convex optimization form. So here, AI is basically the feature vector. So for any given x, think about AI prime x is exactly the output of this three-dimensional third-order polynomial, what it predicts. And I have some data points which tells me what the actual temperature is at that point, what the actual electricity demand is at that point. So this, you can view each of this component as an error between what my model predicts and what the data currently I have says. So you look at all of these errors over all possible data points, and you try to minimize this error. You try to find the best x0, x1, x2, x3, such that that model fits the data the best. Best in the sense of minimizing the prediction error. Okay? So you can formulate many different problems. You have some data set, you come up with a model class you would like to use to explain this unknown input-output relation. You put it in this format to be able to come up or find the best model parameters. Or you want to train the weight vector parameters of your model to be able to minimize this problem. So this is basically, actually it has a name, empirical risk minimization. This is a very popular formulation in machine learning. So what we want to do is algorithms to solve this fast. Of course, the example I gave you is baby, right? It has just 4 parameters that we're trying to figure out. In general, think about maybe a classification problem where you have 800,000 news stories. They have features, these AIs, which are 50,000 dimensional. You want to classify these stories according to what features they have into different classes. Is it economics? Is it political? Or what kind of news story is this? You formulate it this way. But in that case, the sum you're taking is over 10 to the 8 different data points you're considering, and your x is 10 to the 6. So how do you solve this problem? Formulation, I think, is pretty straightforward. The question is, how do you come up with the optimal value for this 10 to the 6 different parameters? Okay? So that's the excitement. If you look at, we now have algorithms that can solve these problems very fast. In particular, I will call them incremental methods, but there are more popular names. I will tell you the popular names as well in a second in machine learning. Why are they incremental? Remember, the gradient, I told you these are very simple gradient methods. Take the gradient of the cost and then update your decision vector along the gradient. The gradient is a sum over all data points. You have to be able to make one step, you have to go through your 10 to the 8th data point at each iteration. You don't want that. So incremental means instead of this full gradient, I actually make steps by using each of the data points incrementally. I take one data point, data block, I take a step, I update my parameters. I take another data point, I make another step that will hopefully allow me to do progress, okay? And because these are incremental in a way that processes data in a sequential manner, they're also very sort of amenable to distributed decentralized implementations and even works with dynamic online data. If the data keeps coming in, you don't have it all in one place, but it keeps coming in a dynamic fashion. You can use these algorithms because it works with one data at a time, one data block at a time, okay? So you're trying to solve this problem. You want to sort of only use one of these FIs at each iteration. But then an important consideration is, which FI are you going to pick? So you want to implement this algorithm. You have F1, F2, F3, all the way to F to the million. Which of these Fs are you going to take first? And that's an important consideration in thinking about how to design these algorithms. You can do something deterministic, 1, 2, 3, 1, 2, 3, 1, 2, 3. You can do something random. At each point in time, you can look at your data, pick a data point randomly, and process according to that. Or you can do the random one is called the stochastic gradient descent. And another way of doing, for instance, you get this iteration, you pick randomly one of these functions from 1 to 3. So it could be 2, 1, 1, 3. At each point, you're picking a random data point. Or at each iteration, you can come up with a random cycle and process according to that cycle. You're done, you pick another random cycle. And that's the so-called random reshuffle. And you may be wondering, so what is the difference between these things? Why does it matter? Well, this stochastic gradient descent, the one that I just showed you, this randomly picking the data points, is the most widely used method in the machine learning practice. So they are extremely popular, and the method that's used in the deep learning applications, deep neural networks that you may have seen for image classification or other problems. This is the default method for data analysis that's used also in industry. And in terms of the research, there's a large sort of set of works that sort of focused on understanding properties of this algorithm. The important thing is SGD has a runtime which is independent of N and M. Okay? It doesn't produce accurate solutions, but it produces sort of approximate, good solutions very fast. That's what I want you to remember from this. It's a very simple algorithm, and basically it operates very fast on these large instances. So let me just maybe in the next 2-3 minutes go a little bit more mathematical, but I just want to highlight our work in this area. So SGD is studied a lot. The random reshuffling, the one that picks cycles randomly, less so. Only empirically there are some papers that shows that random reshuffling is very fast. So this is an example from a famous paper by Bateau, which does a text classification example. This is a very large example. And then applies SGD as well as random shuffle, and shows that random shuffle, actually reshuffle, is very fast compared to SGD. And nobody knew why. I mean, if you look at Dimitri Bertsekas's textbook on optimization, here is the code. Well, this is very fast. In practice, we saw that it is fast, but establishing this analytically is difficult. It's an open question. So it has remained an open question. Why is it difficult? Randomness, right? The first one, SGD, picks randomly at each point in time independently. Every sample is independent. That is easy to analyze. When you take a probability class, you will see that that's easy to analyze. The problem with random reshuffle is you pick a random cycle, and that makes everything correlated. So that correlation makes it very difficult to analyze analytically. So Okay, I'll skip this very fast. We have a paper that analyzes this and proves that it is indeed faster than SGD. So just to compare, this is the paper that shows that the SGD has a rate of 1 over k, k being the iteration number. And we showed basically that it is 1 over k, random reshuffle is 1 over k squared, provably. So dimension independent, and it goes with rate 1 over k squared. So if you're thinking about a solution which is, let's say, error tolerance 10 to the minus 4, basically we're talking about SGD finding it in 10 to the 4 iterations versus 100 iterations for random reshuffle. So that's the difference. And we have some examples which shows that actually this is our algorithm, which finds it after 1,000 iterations, sharp. The other one is still trying to come up with a solution. Okay, so how am I doing with time?
We have another half an hour.
Another, okay, I can go very open loop though.
Q&A.
Okay, very good. So please interrupt me at any point in time. We don't need to do it at the end. So if you have any questions, I'm happy to take questions also in the middle. So let me now talk, this was about how do you do fast algorithms for large problems, right? Another idea is what I mentioned. Much of this data is distributed. So it's not in one place. How can we come up with algorithms that can process this data in a decentralized manner? You have data stored in different places. How can I come up with an algorithm that can actually process this? So my argument is that the incremental methods that I just showed you can also be used for distributed algorithms. So for instance, I can actually think about the easiest one as a distributed algorithm over a ring of processors, maybe a sensor network where the sensors are configured according to a cycle. And why is that? How was the SGD or incremental method working? Taking one data block, processing, going to the other data block, processing. Now assume that each of these different data blocks are in different sensors. So you can actually think about the same operation as this sensor takes the decision vector, the parameters, updates according to its data, moves to the next sensor, updates its decision parameter, moves, and so on. So it could be basically the cyclic structure of incremental fits very well with a ring of processors. If you have maybe sensors that are configured according to an arbitrary network, then you can think about randomized versions of this. So you can say, okay, this processor processes its data, chooses the next processor randomly, and then moves the outcome of its processing to the next node or processor. And you can actually develop algorithms in this way and show that even though all this is done in a very uncoordinated way among processors, at the end you will find a global solution as if your data was in one place. And in many times as fast. So that's sort of an exciting point. I'm not going to show you, we have developed a lot of distributed algorithms for this, but I'll just show you one idea. So this is, again, the problem we're trying to solve. Each of the FIs are in different processors. And we actually assume that these are connected by a time-varying graph. So these could be robots moving around, collecting data. And their connectivity structure keeps changing. At this point, I'm connected to Bob. At the other point, I'm connected to someone else over there. How would you optimize all this data in a way that you make use of the entire data set? So the idea is basically you can come up with methods which do local computation and communication with your neighbors in a time-varying manner, yet still at the end optimize the central as if all the information was in one place, and do this very fast as a centralized algorithm. So that's the challenge. How would you do this decentralized processing over a time-varying connectivity structure, making sure you communicate and compute at the same time? So that's sort of you can use this idea to come up with different methods and algorithms and solve the global optimization problem. I'm not going to go into the details of different methods, but there's a lot in there. So I've talked to you a little bit about these data processing algorithms. Let me now give you an idea about how do we think about dynamic control of contagious processes on networks. And when I say contagious processes, again, I'm using this very broadly. This could be epidemics where, a particular epidemic is moved from person to person through a contact social network. It could be a security attack where a virus is going from a computer to another computer by malicious emails. It could be financial risk, so inability to pay back debt or liabilities of a financial institution spreading from one unit to the other, and many others. And the fundamentals here is that there are local interactions. Interactions between different agents are local, dependencies and contact. And this network, complicated network, is what governs what happens globally. Okay? So you want to control this system, and you have limited resources. How do you do that? So let me just give you a couple of news clips to show you that this problem arises a lot. So this is from New York Times. You have limited number of vaccines. You would like to administer it in a way that sort of minimizes the epidemic or the spread of the epidemic. So how would you do that? Another one is supply chain disruptions. The global supply chain is completely connected. Anything goes wrong in Japan, you can feel it in Europe immediately. So this is another clips which says basically that these disruptions, supply chain disruptions, is a major threat. How do you use some dynamic intervention mechanisms to minimize the damage? Here's another one. Again, the systemic risk to the financial system, very much motivated by the 2008 financial crisis. How do we take action? And most of the literature focuses on static control mechanisms, looks at the connectivity of these financial institutions, banks, looks at a particular bank. Well, this looks like the most important bank here. If I actually protect and make sure that its liabilities remain intact, hopefully I will save the whole system. But in many applications, you actually see the dynamic progress of this contagion process or the spread. Then the question is, how do you actually design dynamic control policies? You know that this epidemic is spreading. You would like to contain it with limited resources. So, okay, I'm not going to present the details of this, but just to tell you that we can actually, the goal of the research program here is to come up with algorithms that are efficient. That means, operates fast, and also optimally contains, using limited budget, this kind of epidemic. And for instance, I put one result which shows that there's a policy called cure policy that we have developed. This is actually only uses a macro property of a very complicated network. This is a cut width of a graph. So you have million nodes here. The cut width of that million node network can be computed efficiently. And just using that single parameter cut width, you can come up with a policy. And this theorem says that that policy is optimal. And you actually can say which graph or which network can I contain the damage of this epidemic, and which networks I have no choice. This will actually the damage that we will incur will be very critical in such networks. So basically, this theorem says when is rapid curing possible, and what should we do to do the rapid curing, okay? And the point, again, is, if you're thinking about what to do optimally on this network, that's a very hard concept. The idea is, can you come up with some macro properties which will design your control algorithms? And here is some practical performance of the algorithm we designed. So this is the curing budget, and as a function of that, how quickly can you control or extinguish this epidemic? If you use like a degree-based policy, this is how quickly can you do it, versus the cure policy. And you see that that's much faster than, this is just a simulation. And then we weren't sort of convinced, and we wanted to use some real data to see the performance of this algorithm. We basically got some data from the Center for Disease Control. This is for the H1N1 virus. This shows in Massachusetts how many vaccines were administered, and also as a function of time, and how many people were infected, okay? And we did this exercise. They used whatever policy they used to decide how many vaccines they would like to deploy. We said, okay, I'm skipping some details. Let's actually use our policy. If they had used our policy, how quickly would they be able to cure this epidemic? And this is basically the outcome. Had they used our algorithm, many less people would have been infected. So this is sort of...
Are they using the algorithm now?
No, this is just the data we got. But I mean, this is actually a master's thesis of one of my students. And it was very surprising and impactful for us. So, you have, I think the point I'm trying to make is, although it looks very mathematical, what I do, the impact, especially on problems of importance, could be huge. And thinking systematically and in a principled manner about some of these very, hard-looking problems can actually lead to a lot of benefits for the society. Okay, so that's what I wanted to share with you. So I also said something about game theoretic models and economics, right? And you may be wondering, where does that fit? So I don't have time to go into the details, but I just wanted to pick 2 examples of where we use game theoretic models in similar questions. The first one comes from traffic. And it's about, of course, how do we control congestion? And I don't know. This was actually a real pain in my life, and that's why I started this project. I drive my kids to school every morning, and in a very heavy traffic. I am, basically live attached to Waze or Google Maps. So, that motivated me to start thinking about this problem. And there's, of course, a large community that thinks about traffic, transportation systems. Many schemes to be able to actually ease congestion, right? There are these penalties, some tolls, restrictions. There's some new systems deployed in India where traffic is really pain, based on reward mechanisms. There are some apps that propose some coupons or rewards if you actually leave home at 7 instead of 7:30 or at 9 instead of 8:30. So some rewards for actually avoiding rush hour. So many people are thinking about this. How can I actually ease congestion? And as I mentioned, Waze is one, or information. Providing information to drivers, commuters, is one way that is very popular now. So these apps are new, used widely, yet how they actually ease congestion is a question mark. We don't know, right? I didn't bring it here, but you may be reading a lot of articles in newspapers about its impact, negative impacts of using Waze on various roads and various different neighborhoods. So the question we wanted to ask was, can we formulate this, and can we actually come up with a systematic answer to what would the impact of Waze be on congestion? Okay. Now, to be able to even tackle that question, you have to first figure out how commuters make road choices. You're given a network, you're given a set of commuters. Okay. So the first question is, how do these commuters make route choices given the information they have? So you provide them information about 2 roads, 3 roads, 5 roads. How do they select routes, right? And that's where game theory is important, because this is a multi-agent problem now. Because every commuter is different. You want to go to work very quickly. The other person doesn't care as much. One person is leaving its kid, very important, you can't be late. So anyway, the point is, everybody's decisions are decentralized, autonomous, and depends on what their objective is. So that's where you actually first use a game theoretic model to capture how commuters make route choices given a particular information structure, given a particular incentive structure. And once you can actually write that down, you can then start asking questions about, how do I design Waze? How should I provide this information such that it is actually good for a subset or all of these users? Okay, so that's how game theory plays an important role. Another one is this notion of risk. I kept talking about financial systems. The 2008 financial crisis left much pain as well as many questions for people to think about. It started from one of the financial institutions having issues being able to pay its debt and spread to the whole system just because of that one financial institution. So this is the so-called systemic nature of these spreads. The system gets a shock in one small unit, a small shock. But because this system is interconnected, I owe Bob some money. He owes another person some money. The minute I can't pay him, he can't pay the other person. So this basically amplifies the nature of this small shock, makes it bigger and bigger, and creates this domino effect. Okay? So that's another place where, again, game theoretic models are important. So what we do is, for these different applications, we try to say which network amplifies the risk, which network actually makes it die down very quickly. And if it's amplified, how can we control it? Can we actually make sure, just like the epidemic example I gave you? But of course, all of this, there are many models people are using to address these questions. My principle is always, if you're addressing a question in financial systems, you need to really understand how these financial systems work, how different institutions are coupled through these debts and liabilities. So you have to really understand the problem to be able to come up with the right model. An epidemic model, dynamic model, is not the same as a financial system, risk spreading in a financial system. Okay, so let me wrap up there. So this is basically about a very sort of research program, broad research program with lots of questions. I like it because it combines ideas from not one but several disciplines. It gives me an opportunity to talk to and interact with many different areas. It's very interdisciplinary in nature. I talk to economists, I talk to finance people, I talk to people in transportation. So there's a lot of coupling and nice ideas that come together. And I hope I was able to convey that while it's math, it has a lot of impact. Okay, so with that, let me conclude. Thank you. Yes.
So back in your example, you mentioned that the quantitative descent is still the primary model that is machine learning.
SGD?
Yes. But you also showed that there is some evidence that you have been jumping into coefficient.
Yeah.
If that's the case, why haven't you adopted what?
Because that's actually a very good question, and that's a question of interest that people are thinking about. What I showed you was a performance of the algorithm for solving that particular optimization problem. SGD has other properties that make it very appealing. In particular, I talked about convex problems, right? Actually, many of those deep learning problems are non-convex. That means that we can't expect the gradient algorithm to find the global optimum for us. Yet, SGD does something magical and finds it. So that's actually a huge area now. Why is SGD performing so well on these over-parameterized models, although they are non-convex? And similarly, it's not just about training your model. The generalization properties are very important, meaning when you get the new data set, it should predict as well as what you trained your model on. SGD somehow has also very nice generalization properties. So maybe it was misleading. What I showed you was just one aspect of the comparison between two methods. There are many other considerations, but that's a very good question. Yes?
Can you explain the function of the bias unit and the parameters, what and how it improves from?
Tell me again. The what?
In your list of parameters, you have all your parameters listed, but you also have that one, just the number one as a bias unit.
Yeah.
Can you explain to me how that actually works?
It was just one example. I mean, depending on the example, you can train different models. So I'm not talking about the effect of bias here. So there's some different aspects that we can talk about, effect of bias, variance, but this is not what I was trying to highlight here. Okay, good. Sorry. I can't hear you.
Oh, sorry. So can you explain in the incremental gradient method between the with replacement and without replacement
The difference between the two algorithms? So remember we had this sum over 1 to 100, let's say. We have 100 data blocks, and we want to basically our incremental method goes through 1 to 100. That's one cycle, and then you do another cycle. right? So in SGD, at each iteration within the cycle, you pick something randomly. You pick one of the components randomly. So it's a random pick throughout. In the random reshuffle, you're at the first, you look at one cycle, you get a random cycle. You get, you get 1 to 100, a random permutation. And then you process according to that random cycle. You go to the next epoch, you pick another cycle randomly. So the difference then is in SGD, you may be repeating the same, you may be using the same component function or the data over and over, because you may be randomly 2, 2, 2, 2. Instead, in random reshuffle, you touch every data point exactly once in each cycle. So that's sort of the main difference why the tool performs differently. Yes?
So is the only and main difference between stochastic gradient descent and random reshuffling, like the way that you shuffle data people process?
Yeah.
Right. So why does one of them work on, why does random reshuffling not work on non-convex functions, but SGD does?
I don't know. I don't know why even SGD works on non-convex functions well.
You're actually training your models. How do you ensure that the number of data points that you sort of the training set is large enough to sort of be a good approximation, especially when you're dealing with big data, you're dealing with like billions of data points. How do you get like a training set that's pretty representative and good size?
That's a very good point, and there's quite a bit of work. And think about now, I'm talking about large data sets, right? It's too large. Maybe I don't need the whole thing. Maybe I need to prune so that I actually have something much more representative and I can train my data. Will that then generalize well? That's a very good question. It's something I didn't cover here. People do look at these questions.
Obviously, machine learning and especially neural networks are very popular nowadays, but also a lot of people criticize it, and they say that it's only really able to look for like latent features, look for common features in data. Do you think that machine learning and neural networks will eventually gain the capabilities that a lot more like rigorous methods have, or do you think they're going to stay in the realm of just being
Classification
random?
problems.
Yeah.
Yeah, so that's an excellent question. Right now, there's this huge excitement that we're able to do things that we weren't able to do before. But I totally agree with you that right now, moving to the next stage will require us to also think about how robust these methods are. Especially, if you're doing image classification, maybe it's okay to use this. But if you're actually trying to use this in a, self-driving car, would you actually like to rely on these algorithms to put your kid and send them to school? So that's a discussion that's ongoing. I think there's a huge research program in making these algorithms more robust, more understandable, predictions more understandable. And then the second layer of questions is one is about robustness and safety, right? And the other one is about more social aspects, more societal aspects of these. I mean, if you start thinking about not just maybe error and prediction performance as the objective, but also fairness. But also, thinking about what it means for us to use these in many more different applications. So that's a very good question. So far, the applications are, very promising, but there's a huge second layer that we need to, address to be able to make these actually come into our life.
But in the end, do you think that gradient-based methods are going to be, like in 20 years, are we
yeah.
between gradient-based methods or methods you were talking about towards the beginning of the talk?
So gradient-based method is only about its computation. There's also the modeling part, right? So the way I modeled the questions were to minimize errors. So I don't think that's where we will be. But I think to be able to solve whatever problem you formulated, you will be using gradient methods. Yeah.
How do you deal with uncertainty when you're modeling these networks? And have you done a similar study to the H1N1 with your cure?
Yeah. Yeah. Very, very good.
Quantitative easing at the end of the
Yeah. So very good question. was very high level here. Much of these dynamics that I'm talking about are stochastic dynamics. So that's how we incorporate uncertainty. So there are many different ways. We use SIR, SIS models, which are all probabilistic, which actually incorporates the uncertainty in a probabilistic way. And what the result that I showed you is for such a stochastic model, I still am able to come up with this deterministic parameter and come up with a stochastic policy that is designed using this deterministic parameter. But that's absolutely something we actually incorporate into these models. Sorry.
So when you look at epidemics and financial data sets, do you encompass like national scale or global scale?
So both. I mean, I think it's a very good question. So I generally work on the theoretical models, but I'm trying to use more and more data sets to actually see the impact. And it's a huge question to actually find the right data set to be able to, for instance, I talk about financial networks. What is that? Is it the banks in US? Is it global? So being able to come up with good data sets is another important aspect of this research program. I mean, the ones that I showed you was in epidemics was in Massachusetts. We have had some other work where we actually got data from the entire US, from all states, so that we can actually look at the couplings between different states. So you start small and then try to expand. The relevant thing is, of course, at global scale. Some of the work on the economic data, that was US scale, but some of my collaborators went on actually to look at the global supply chain as well. So all of these are relevant, is what I'm trying to say. Some of them are intra-effects, some of them are inter-effects, and you try to capture through different models and the data set you have. Sorry, yes.
What exactly are the disadvantages and advantages of using decentralized optimization methods with decentralized optimization?
Oh, that's a very good question. So the reason we're interested in decentralized is sometimes we have to, right? You have a decentralized sensor network, data is collected in a decentralized way. Or, it's so large that you can't fit it in one processor, so you actually store it in a decentralized manner. Now you have to process it in a but of course, what architecture to use? It's still a question. Do you do it completely decentralized, or do you maybe have a master processor which allows you to coordinate these? So depending on the application, whether you can have that master processor or not, so what's the right communication architecture? That's another good question. And in some cases, people actually prefer not to have a master processor, because that means you're going to be sending data, and sometimes because of privacy issues, you don't want to do that. So different applications and different considerations make you think about different kind of communication protocols that you impose on your problem. Sorry, just this and then, yeah. Yes?
So you made the distinction earlier between faster but less accurate algorithms and then more accurate but slower algorithms.
Mm-hmm.
Is it possible to use a faster algorithm and then refine it with a more accurate algorithm?
Excellent question. That's what we're trying to do now. Actually, what we're trying to do is, in the last 6 months, we have a project which thinks about, not just faster, but let's now add robustness and faster together in the design criteria. So don't just do convergence rate, which is what we've been trying to do for the past decade, but try to come up with algorithms which are both fast and robust. So it addresses some of the questions, not just look at convergence rate, but also put robustness into the design phase, as opposed to something that comes as an afterthought. So that's what we're trying to do. And we have some nice results, which I can show you in terms of, if you're thinking about noisy information, and if you're thinking about generalization, actually you have to do this design with this robustness and rate criteria simultaneously, and you'll get surprising results.
So with multi-layer neural networks, oftentimes when you finish training, it becomes this sort of black box where you don't really understand how it works so well and why it works so well. So is there any effort on this end to kind of
Yes. Yes, in our department, we have faculty who actually look at that question, interpretable machine learning, especially in the context of deep learning. Why was this prediction made? So that's not my work, but there are people who work in that area. Wow, good. That's a complete different area, but that's another one our department is excited about and thinking about. So right now, I think we're still seeing the technology developing to make it, possible to do simulations or optimization in a fast, you're changing the computational model, right? We're not there yet, but I'm very hopeful that we will actually, build the quantum computer and they change the computational model and rethink these questions. But that's way beyond my talk here. Well, I love the questions. Maybe I'll, at the end, can I just talk to people? Maybe I'll recruit some people to my group at this point.
Sure. Good. I have one more question. Anybody? Oh, there's one. Yep.
Have you had any trouble getting your data sets ever as there like new privacy laws coming up like HIPAA and stuff?
So I have not run into it, but I know people do. So I think right now MIT is in the process of coming up with institutions. We have this new IDSS, and we are actually carefully working with people who have the data to be able to have access to those data sets. So it's an issue, but I think so far we haven't run into I haven't run into a block that and doesn't allow me to get the data that we want. But it's definitely an issue. Getting the data, I was answering actually someone, getting the right data is crucial, and that's something that we should definitely think about. How do we do it in a way that's respects privacy yet enables this line of work?
Okay, so that's...
Thank you.
Can I have two from CogWorks for the presentations? Come on. Come on now. You know the drill?
Thank you.
So,
It's a shirt.
Wow.
so we have a little presentation. So thank you from the class.
Thank you.
So I think you can actually come down and ask for some questions. But before that, I have a couple of announcements. So how many of you know what you might want to do next summer? I know this is long, it's far into the future. But do you think some of you might be interested in a potential internship opportunity for the summer, paid internship opportunities? Yes? Okay. So it turns out that one of our platinum sponsors, Raytheon, has agreed to make two internship opportunities be available to the BWSI graduates, and it's the research lab in Cambridge. So the announcement will come out later today, and then you have about a week to apply, and then they'll make the selection by end of the summer. So, when you say two, that means two people. Correct. Well, let's see. If there are more qualified candidates, maybe I can twist their arm a little bit. Matter of fact, you can ask the question when they come to give their talk next Thursday. Yeah. So, all right. With question? Yep. Correct. So actually, tomorrow is with Lockheed Martin. This internship is with the Raytheon, and the Raytheon dinner event is next Wednesday. There is one tomorrow. That's with another company, by Lockheed Martin. Yes, we'll send out the emails. Yeah.
Thank you, Bob.
It's lunchtime. So what's the routine? Usually the front? No, actually, do you go by the class? Okay. Whoever can yell loudest, I'll pick that group first. Okay. I heard CogWorks first.